Hello again. So at the end of the last video series, lectures 2, I lied a little bit. I said the next video is going to talk more about geometric series. I think we're just going to mention a few facts about series before going back to geometric series. So in the first series videos, we talked about what it meant for a series to converge. In the second one, we introduced the concept of a geometric series as a nice example of series that we can tell if they converge or not. We're going to go back to working with them. But let's just make a quick note of a few quick facts. So let's suppose we've got two series that we know converge. The series whose terms are these AIs and the series whose terms are these BIs. And suppose C is a constant. So notice that my lower index here is M. The only assumption on M is that it's an integer. So we're going from M on up, right? When I defined series, M was equal to 1. We started at 1. In geometric series, the formula we came up with, M was equal to 0. Really, I can start at any integer. So I'm just making this as general as possible. So what does it mean for a geometric series to converge? Well, it means that the limit of the partial sums converges to some finite number. So let's look at this new series. C is a constant. I'm going to look at the series of whose terms are C times AI. So I know that some of the series AI converges. So what happens to the series C times AI? Well, if that converges, that equals there is if it converges. If this limit is finite, it's equal to the limit as n goes to infinity of these partial sums. Of course, n we're thinking of is bigger than m here. And how do we rewrite the limit of the partial sums? Well, partial sums are just this, right? I just expanded it. And what's common to each of those terms? Yeah, you're right, there's a c. Because c's constant, it doesn't change with I can factor c out. And I get the limit as n goes to infinity of c times the sum of those a's from am on up. Of course, I can then, c doesn't depend on n either, so I can factor c out of the limit, right? I get c times the limit n goes to infinity of the sums of those a's. And I'm going to write that now as the sum I equal m to n of the AIs. And of course, what's this limit? Well, this limit's equal to that series that we are assuming converges. So we're assuming that limit is finite. And since that limit's finite there, since this limit is finite here, the limit with the c is finite. Therefore, this equal sign holds. So in other words, what can I do? I can factor a constant out of the series. If I've got a constant times every term in the series, I can factor a constant out. Okay, so let's go down to this item 2. So now I'm adding the terms of the two series, and I've got this new series. And I really want to understand what's happening with that. And again, by definition, if this limit over here is finite, then this by definition converges to what that limit is. But let's analyze that limit. That limit is, I missed a parentheses here. That limit is, well, I can expand those terms, right? That's the sum n goes to infinity of just expanding them all out. And we've got the commutative law of addition, which says I can rearrange the terms. I can write that as the limit as n goes to infinity of what I get when I group the a's and group the b's. am plus all the way up to an plus the sum bm all the way up to bn, right? And the thing is these are the two partial sums, right? And I'm assuming that the limit of each of these is finite, so I can separate that into two limits. Limit n goes to infinity of the sum I equal m to n of ai. That's if all these are finite, I can separate these. Sum I equal m to n of bi, limit. And of course, those limits, we're by assumption converge to sum I equal m to infinity of ai plus sum I equal m to infinity of bi. So again, this equal sign held if that limit was finite. This limit here is just another way of writing this. which is another way of writing this. And this equal sign holds if both of these limits are finite, but by assumption, those limits are this, which are finite. So everything's finite. So this can be separated into that. In other words, I can separate a series into the sum of the two series, a series whose terms are added into the sum of the two series, assuming I know they both converge. This is important, assuming they both converge. We'll have examples later on of when they don't. But let me just point out, in fact, we've got a little bit more. If I had a minus here, that would also work. You'd have a minus, minus, minus. But when you rearrange the terms, you could factor out a minus. I'd have a minus in there, a minus there, and a minus there. So I can separate sums and differences. Question, do you think I can separate products? Quick, what do you think? The answer is no. I'll let you guys think of an example at home to show that. Products and quotients cannot be separated. That's a big, big no, no, no. But sums and differences can be, and constants can be factored out. Okay, next one, we'll go on to more geometric series.